Geomagnetic storms are significant disturbances in the Earth's magnetic field caused primarily by solar activity. When the sun emits bursts of energy and charged particles, often during events such as solar flares or coronal mass ejections, CMEs, these particles can interact with the Earth's magnetic field, resulting in fluctuations. The implications of geomagnetic storms extend beyond mere scientific curiosity. They can disrupt satellite operations, communication systems, and even power grids, as well as produce breathtaking auroras, such as the northern and southern lights, caused by charged particles colliding with atmospheric gases. To understand geomagnetic storms, we first need to explore solar activity. The sun is a colossal ball of hot plasma that constantly releases energy and particles into space, forming what is known as solar wind, a continuous stream of charged particles, primarily electrons and protons. During periods of heightened solar activity, the sun can unleash powerful solar flares and CMEs. Solar flares are sudden bursts of radiation resulting from the release of magnetic energy associated with sunspots, while CMEs involve large expulsions of plasma and magnetic fields from the sun's corona into the solar system. When these solar phenomena occur, they can significantly increase the intensity of the solar wind, affecting the magnetic environment around Earth. The Earth is enveloped in a magnetic field generated by the motion of molten iron in its outer core. This magnetic field serves as a protective barrier against solar and cosmic radiation, deflecting most charged particles from reaching the planet's surface. However, during geomagnetic storms, this protective shield can become temporarily disturbed. When solar flares or CMEs direct streams of charged particles towards Earth, they can collide with the Earth's magnetic field, leading to sudden fluctuations that characterize geomagnetic storms. Geomagnetic storms are classified based on their intensity, typically measured on a scale from G1, minor, to G5, extreme. G1 storms result in minor disturbances, causing slight fluctuations in power systems and affecting high-frequency radio communications. G2 storms are moderate, leading to voltage irregularities in power systems and an increase in auroral activity. G3 storms are categorized as strong. They can significantly disrupt satellites and radio communications and may cause power grid fluctuations. G4 storms are severe, potentially leading to widespread voltage control problems and transformer damage. Finally, G5 storms are extreme events that can cause widespread blackouts and severe satellite disruptions, impacting essential communication and navigation systems. The effects of geomagnetic storms are varied and can be profound. One of the most visually stunning effects is the auroras, which are beautiful displays of light seen in polar regions. These lights result from charged particles colliding with gases in the Earth's atmosphere, creating bright and colorful displays. However, the impact of geomagnetic storms extends beyond aesthetic phenomena. Satellite operations can be severely affected, as increased drag and radiation can disrupt electronic systems, impairing GPS and communication functionalities. Furthermore, fluctuations in the Earth's magnetic field can lead to voltage changes in power grids, potentially resulting in outages or damage to transformers. Radio communications, especially in high-frequency bands, can also be disrupted, affecting aviation and maritime operations. To address these challenges, monitoring and predicting geomagnetic storms have become crucial. Organizations such as NASA and the National Oceanic and Atmospheric Administration, NOAA, actively monitor solar activity and provide forecasts regarding geomagnetic storms. They utilize a combination of satellites, ground-based observatories, and sophisticated computer models to predict when storms might occur and their potential intensity. This proactive approach is akin to meteorological forecasting, allowing for timely warnings and preparations to mitigate the impacts of these disturbances. Preparing for geomagnetic storms involves enhancing resilience across various sectors. For power grids, upgrading infrastructure to withstand fluctuations is vital, alongside implementing protective measures that can minimize risks. Satellite design is also crucial. Developing more robust satellites capable of withstanding increased radiation and magnetic interference can safeguard vital communication and navigation systems. Public awareness plays an essential role as well. Informing communities about potential impacts and appropriate responses can help mitigate risks during extreme events.